Sugar Sugar is a classic flash game all about getting grains of sugar into coffee cups by drawing arbitrary lines with your mouse. The concept is so simple that by level 2 you're already familiar with the core mechanic. As a developer, games like these often make me wonder how it was done, or how I would go about making something like this. In the case of Sugar Sugar, the game is simulating up to 3,000 grains of sugar every frame. Not only that, it has to check collision against hand-drawn obstacles, and it has to run decently on the computers of the time. My instincts told me that there's no way you could achieve this by actually iterating over 3,000 individual objects. So, I decompiled the code, expecting to find some clever trick, perhaps even a simple fluid simulation, only to find some of the most spaghetti-filled code I've ever seen. The entire game logic sits in a single class, which, when decompiled, takes up over 3,700 lines of code. On top of that, it turns out that the sugar logic really is just one big dumb loop. Let me break it down for you. Every grain of sugar moves down at a constant speed of 1 pixel per frame, with no acceleration from gravity. In most games, the lack of acceleration on a falling object would make it feel unnatural, but since these are grains of sugar, I suppose the implied air resistance makes up for that. On top of this downwards motion, there's also a random horizontal sway, up to 1 pixel in either direction. These two are the primary factors that determine where the sugar is going to end up on the next frame. And that, of course, is used for predicting collisions. This is where the game does admittedly come up with a pretty clever trick. In order to detect a collision, the code checks the color value of the pixel at the candidate position. If it's below a certain level of brightness, the sugar is allowed to pass. If it's above that threshold, a collision is flagged. That's why every level has a dark background with brighter highlights. In fact, if I just switch to a brighter color palette, the sugar never drops. To resolve this collision, the game drops the candidate position and instead checks for free space on either side of the current position. The sugar grain then moves in the direction with at least 2 pixels of clearance. And with that being the whole algorithm, I guess it is simple enough to make it viable for the average school computer in 2011. There are some fancier mechanics in the game, such as a button to invert gravity or holes that magically teleport the sugar, but those are relatively simple features that don't change the core physics of the game. With that in mind, in spite of the rancid codebase full of duplicated code that requires a map to navigate, I really can't blame Sugar Sugar, because a simple one-off flash game doesn't need clean code, and I guess it was still cool to see those bitmap hacks for collision. Now, this got me wondering about other Flash games with technically impressive mechanics, so I put out a YouTube community post asking you all for ideas on where to look next. Of course, right off the bat, there were a few mentions of Portal the Flash version. Given the branding of this channel, that does make a lot of sense, so let's take a look. Now, the teleportation mechanic isn't that interesting on its own. The simplest way to teleport something in a game is to just set its coordinates. But, of course, when implementing portals, things aren't that straightforward. At the very least, you have to be able to redirect velocity. After all, when Speedy Thing goes in, Speedy Thing comes out. Valve implements this by translating your velocity vector to the new reference frame. This is universally applicable and keeps the behavior of portals consistent. The Flash version, however, has hard-coded behaviors for each of the 4 cardinal directions. This is why you won't find a slanted portal surface. The engine simply doesn't support it. Yes, this simplifies the math a bit, but that comes at the cost of less flexibility and more duplicated code. Now, it's not really that hard to rotate a vector, especially in 2D, but I get the feeling that the developers of this game just weren't as familiar with the math involved. Also, notice how in Valve's implementation, objects near a portal are duplicated on the other side, making you feel like you're actually moving between portals, not just teleporting. This is what lets you have 2 halves of a cube in different locations, despite there only being 1 cube. The Flash version doesn't bother with this. Instead, as you step through a portal, the collision for the respective wall is overwritten, and your jump key is disabled until you've fully gone through the wall, at which point you simply get ejected out on the other side. That said, the other portal does react somewhat by rendering a blurry figure of the player as they approach. This is an imitation of how Valve's portals render what's on the other side. Valve does this by masking a separate camera onto the face of the portal, but the Flash version's approach is a lot more primitive. This is just a blurry copy of the player sprite. I went ahead and unblurred it in the game code to better show what's going on. In many cases, the sprite is actually upside down, and in other cases, it's also moving the wrong way. Notice how here I'm jumping up, yet the sprite is moving down. Granted, this is normally just some subtle visual flair, but it just goes to show how hard it is to make portals the way Valve did it. After all, one of the main reasons they hired the Narbacular Drop team is because they had already figured out all of the complicated math. I'd say that at least a part of these discrepancies can likely be attributed to the Flash version team's inexperience in developing something like this. There's a lot of duplicated code here, which is a red flag in almost any code base. And actually, here's a good example of why that's the case. This is the code that handles collision near portals. Feel free to pause the video and see if you can spot the mistake. Got your answers ready? Alright, now the word addition is misspelled in all of these variables, but that on its own isn't really a problem. Code mostly doesn't care about English grammar as long as you keep the naming consistent. But here, on this one line, the misspelling is further misspelled, missing the letter A. One consequence of this is that you can jump on the edge of a right-facing portal. I always thought that this was intended behavior, but if you try to do the same thing on a left-facing portal, you'll just fall right down. And if I patch the code to fix this bug, the same thing now happens on both types of portals. While this ultimately is just a silly typo, it would have been easier to spot if these calculations weren't duplicated and hard-coded to specific angles. In that case, it would have been obvious if something didn't work quite right. But with the way it's implemented now, the developers only have a 1 in 2 chance to spot the issue. Now, if it seems like I'm being overly critical of these games, you're probably right. Every game has nasty code. There's a reason why developers almost never make it public. As long as it's fun to play, the rest is just a means to an end. Keep in mind that Flash was at its peak during an era of the internet where programming knowledge was rare, yet it often took just one passionate developer to create what we now regard a classic. Things have changed since then, and programming has become more accessible. Of course, for creativity, you've still got your heart. But for code, there's Kodi.tech. Kodi is the sponsor of this video, and has been for a few other videos. Since then, commenters have been quick to point out that it's basically just Duolingo, but for code. And yeah, essentially that is what you get. Structured and interactive lessons on whichever programming language you want to learn. But unlike Duolingo, where a year-long streak means you've learned basically nothing, Kodi teaches you how to write real programs by like lesson 10. I've actually been using Kodi to learn the Rust programming language, and I'm now looking for a project in which to apply that. They're not paying me to use Kodi, and they're not paying me to say these exact words, they're just genuinely that chill. So if you've been planning on getting into programming or learning a new programming language, consider giving Kodi a shot through the link in the description. Oh, and one more thing. Kodi is doing a sale at the end of this month, but since this video is coming out way before that, they're straight up just giving you all a discount code so that you wouldn't have to wait. So, to get 20% off Kodi Pro, use the coupon code on screen or in the description. Coming back to that community post, the most popular suggestion by far was Run, a series of 3D first-person platformers, with one simple question. How was it 3D? I mean, if you look back to most Flash games of the era, the vast majority used simple 2D graphics, or at best, faked their 3D with pre-rendered scenes. For the longest time, Flash didn't natively support 3D rendering. It does now, but that was only introduced in Flash 10, which came out on October 2008. But the very first Run game was released a couple of months before that. To get to the bottom of this, I decompiled that first Run game. While Run 3 is the community favorite, that one does take full advantage of the built-in 3D. I also figured that starting with a less ambitious entry would make it easier to reverse engineer. But regardless of which version I picked, it was by no means going to be simple. You see, Run isn't actually developed in Flash ActionScript. It's written in Hax, a very different programming language capable of compiling down to a lot of other platforms, Flash included. This is probably an awesome tool for developers, but it makes decompilation a nightmare. Hax outputs bytecode, avoiding the need for verbose ActionScript. This means that in the decompilation, a lot of variables are missing their names, and a lot of code ends up being mangled. It's a lot harder to understand how something works when you're dealing with nothing but cryptic symbols and numbers. If I had to guess, this is what non-programmers think code looks like. Still, I was able to track down the class responsible for drawing the tiles, and fully cleaned it up with comments and everything. But before we get into how this game works, I want to give you a glimpse of what that cleanup process is like. When I first opened this file, I skimmed it to look for any resemblance of rendering code. There are only 3 functions here that retain their names, that being display, getColor, and getMultiplier. Those first 2 sounded promising, and that's what got me to look at this class in the first place. So, with nothing more to go off of, I started at the getColor function. Right away, the function takes in a parameter of an unknown class. But right below that, I see that this parameter has a z property. That not only tells me that this is a vector, but also that it's a 3D vector, and that this function is using the z-axis for depth. That's exactly what I was looking for. Then there's some arithmetic that I have no chance of understanding just yet, but right after that, there's a call to another unnamed function. Upon first glance, this might seem just as indecipherable as everything else, especially with all those random numerical constants. But hold on. I recognize those numbers. Those are powers of 2, and more specifically, they're bit masks for the lower 3 bytes of a 32-bit integer. In the context of color, these masks are often used to filter out individual color channels. With that little bit of insight, we now have our first fully deobfuscated function, which I'll call scale color. It takes an RGB color value as an integer and scales each channel by the given factor. From here, we just have to move backwards. In the getColor function, we now know what this last call is, along with reasonable guesses for the parameters going into it. And now that we know what getColor does, we can continue stepping backwards to find out more from the code that references it. It's a lot like a puzzle. Anyway, that's how I got my deobfuscated copy of the code, and that's why I can tell you that this pretty much sums up all the magic. The 4 corners of each tile are projected onto the camera plane, turning 3D coordinates into 2D points, and after that, it's really just a matter of drawing a flat shape from those 2D points. That's why the walls have this blocky gradient going on. It's not as much a stylistic choice as it is a limitation of the fact that these are 2D shapes without any real 3D shading. The player is also not a 3D object, but rather an animated 2D sprite, though I guess that one was probably more obvious. But if it's all just fake 3D drawn with 2D shapes, then how did they do the screen rotations and collisions? Well, while the rendering code is faking the 3rd dimension, the rest of the non-rendering code doesn't have to. As far as I can tell, most of the gameplay-focused stuff uses 3D vector math and trigonometry extensively, so in that regard, it's not much different from a game engine today. The math doesn't care how many dimensions you use, so as long as you have a way to render in 3D, the rest becomes trivial. Another game that was brought up in the comments is Interactive Buddy, a weird kind of sandbox where you get to play God with this boxed-in sphere creature. I'm not exactly sure what the ethics of this whole situation are, but either way, that's not what we're here to discuss. The commenter who brought up this game mentioned that it features its own scripting language. I have seen this game before, but I had no idea you could write code in it, so naturally I had to take a closer look. Once again, the entire game code decompiles to a single 9,200 line file. Though, because this is only a reconstruction of ActionScript 2 code, there's no way of knowing whether the game was actually developed this way. True to the claims, one of the first things we find is an initialization for the scripting engine. But while digging through the code does provide a rough reference for the language, the best way to get a feel for it is to write some code. I wanted to find out whether this silly feature is Turing complete. If it is, that would mean that the engine can perform any computation, given enough time and resources. So, to prove this, I decided to write a brainfuck interpreter. Now, I've already made a whole entire video covering this cursed language, but here's the gist of it. Brainfuck is an incredibly simple language, consisting of just 8 valid characters. This simplicity also makes it difficult to use, hence the name. But fundamentally, its design mimics that of a Turing machine, which by definition is Turing complete. In most programming languages, writing a brainfuck interpreter is often a trivial exercise. But in the case of ShockScript, yes, that's actually what it's called, it took substantial effort. Most operations in ShockScript are kind of like Excel functions. There's a name, a pair of brackets, and a few comma-separated arguments. Even an if statement follows the same structure, which is pretty non-standard for a programming language. There's also no way to define your own functions, aside from writing code into a string and evaluating that. And, to top it all off, there are several bugs in the scripting engine. For example, the order of operations is completely messed up. In this if statement, the AND operator applies not to the pair of comparisons as you'd expect it to, but to the operands adjacent to it. Even if you add brackets, it still doesn't work. I found that the only way around this was to create named variables with the value of each condition. But in the end, I did manage to get a simple Hello World program to work from within the brainfuck interpreter. So, hooray! This simple Flash game is Turing complete. Given enough resources and patience, you could eventually use it to run GTA 6. Now, that's all pretty cool, but while looking through the game's code, I spotted something else. Something arguably more impressive than a hidden scripting engine. This game implements its own physics. In most Flash games, the physics are handled by a ready-made physics library that you can just throw into your code, configure a bit, and then forget about. The heavy lifting is done by someone else. What you're currently looking at is Home Sheep Home. I used to speedrun this game, and in my prime, I dissected the code through and through to hunt for glitches and movement tricks. And that's when I learned that many such Flash games use a robust physics engine called Box 2D. For my glitch hunting, that meant that it's unlikely I'd find many physics-related bugs, given that engines like these are often fairly stable. But coming back to Interactive Buddy, this doesn't use Box 2D. In fact, this doesn't use any general-purpose physics engine. It's all in-house code, written specifically for this game, which certainly does some work in explaining the 9,000-line code footprint. If there's any takeaway to be had from digging through the code, it's that this game, and frankly all of the games we've talked about, are a work of passion. Thanks again to Cody for sponsoring this video, and thank you for watching.